Welcome to Brain Vision.
For part A of our question, we're asked to show that at points a distance y directly above its center, the field is given by that expression where b is mu naught I over pi d times the inverse tangent of d over 2y. Assume the strip is infinitely long, and we're going to divide the strips into many thin wires and sum, or in other words, integrate over these. So an integration is just a continuous sum over a continuous function. So I used paint here to draw out a little diagram of what we're talking about, where that infinitesimal change in length is dx. Okay, so the free body diagram that we have here to find the magnetic field is going to make use of the Biot-Sievart law to solve this situation. So as shown in the figure, the current is directed into the page here. And we're going to consider the sheet may be divided into an infinite number of parallel wires using that dx. So consider the small element dx at a distance x from the center of the strip. So that dot there is the center of the strip. So the current then is going to be represented by, or at least the change in current, di, is going to be equal to I over d where d is the total length of the wire, times the change in x, or dx. Okay. And the magnetic field due to this element, or at least the change in magnetic field, dB, is equal to mu naught, which is the magnetic permeability of free space, over 2 pi times the change in current, di, over some distance that we're considering r. So r would just be the distance away that we're considering. So we could go ahead and substitute our di value in above, and what we have is mu naught I over 2 times pi times d times dx over r. Well, from the figure, we can use our that theta value. We can use our trigonometric identity to find that theta value there. And we have the sine of theta is equal to, it's opposite over hypotenuse, right, for the sine of theta using our trigonometric identities. Well, the opposite here is just the distance y that we are divided by the hypotenuse, which would be x squared plus y squared in this situation. So the horizontal components of a magnetic field are equal and opposite. So they're canceled out then. Hence, the net field is going to be due to only vertical components because those horizontal components are equal and opposite. So the magnetic field strength then, B, is equal to the integral of the change in the magnetic field, dB, times the sine of the angle theta. Right? Well, we know what dB and theta are, so we can go ahead and replace those. And let's consider what we're integrating over. Well, we're integrating from, if we go back to this, we're integrating from minus d over 2 because the left side of the wire is d over 2. So we're going to integrate from minus d over 2 to plus d over 2, from one side of the wire to the other, right? So if we go back to our second page here, this would be from minus d over 2 to d over 2. And we can replace dB and sine theta with our values that we have on the previous page here. There's the dB and the sine theta. And dB is mu naught I over 2 pi d times, now we're going to replace the sine theta with y over x squared plus y squared right? Times dx. This is you had that dx left over from the b. Okay, so now we can go ahead and pull the constants out in front of the integration to make this look a little simpler. So what we have here is mu naught I divided by 2 times pi times the distance d times the y on top is also a constant. So what we're left with in the integration, which again, this is integrated from minus d over 2 to plus d over 2. And what we're left with in the integration is 1 over x squared plus y squared integrated with respect to dx. Okay. So you can go ahead and this is a tougher integration. You can, what I did is I just looked it up in an integration table. Just searched for something that looks similar to this to find that out. You might need to use a clever trick like singular or like integration by parts or something like that to solve this if you want. But I just simply looked it up in an integration table. I also think that's equally as acceptable here with a tough integral like this. But what we end up with is this comes out to equal mu naught. So we still have our constants, mu naught I times y still, right? Over 2 times pi times d. And then what does the integral come out to equal? Well, the integral of 1 over x squared plus y squared with respect to dx comes out to equal 1 over y times the inverse tangent of x over y. And then again, these were integrated from d over 2, or from minus d over 2 to d over 2. So there's the top and bottom bounds of the integration. Well, you'll notice that these y's cancel. I'll cancel them in red here. That y cancels with this y. So we simply need to plug d over 2 in for x and then subtract from that minus d over 2 getting plugged in for x in that inverse tangent x over y situation there. So if we plug those values in, and I ran out of room on this page, so I'll start another one. If we plug those values in, what we find is this is equal to mu naught times I over 2 times pi times the distance d. Remember those y values cancel. And then in the integration, this is equal to 2 times the tangent of, or the inverse tangent of d over 2y. So you end up with, when you plug in d over 2 and minus d over 2 in, you end up with d over 2y minus a negative d over 2y, or 2 times the inverse tangent, or inverse tangent of d over 2y minus the inverse tangent of negative d over 2y, which ends up being 2 inverse tangent of d over 2y. So again, we have a couple of things that cancel. You have that 2, that cancels with that 2. And you're left with the answer we were looking for. This leaves you with mu naught times I divided by pi times d times the inverse tangent of d over 2y. And that's what we were asked to show or prove for part A, so we can go ahead and box that in. Okay, now moving on for part B. For part B, we are asked what value does B approach for y much greater than d, and does this make sense? Explain. So when y is much greater than d, what do we have? Well, let's look at our expression for b that we just found. So we see that the y shows up in that inverse tangent relationship. So when y is much greater than d, d over 2y is a very, very small number. So that means the inverse tangent of d over 2y when y is much greater than d is the inverse tangent of a very small number. So we can use our approximation to show that the inverse tangent of a very small number is just equal to approximately that very small number, which is d over 2y. Again, that's only true if y is much greater than d. So now we can plug that into our expression, and what do we have? Well, if we plug that in for our value for b above, we have this is equal to mu naught times I. Now it's multiplied by d, right? And this is going to get divided by 2 times pi times y times d. Okay, well, we can see that the d's cancel. And what does this leave us with? Well, this leaves us with, oops, let's make that a little cleaner. There we go. It leaves us with mu naught I over 2 pi d, or 2 pi y, excuse me, 2 pi y. But what is this? This is simply the magnetic field of a long straight wire. So yes, it does make sense. So we can say this is simply the B field of a long wire. Yes, this makes sense. So we can go ahead and box all of that in as our solution to B. And that's the final part of our question.